morning friends. In chapter 13 kinetic theory, we are going to discuss about the numerical of illustration and also exercise. Already we discussed the two numerical 13.4 and 13.5 of illustration. Now today we are going to discuss the remaining numerical, the illustration 13.8. That is given as a cylinder of fixed capacity 44.8 liter contain the helium gas at standard temperature and pressure. That means in a one cylinder having the volume capacity is 44.8 liter. In this cylinder we fill the helium gas at STP. What is the amount of the heat needed to rise the temperature of a gas in the cylinder by 15 Kelvin? Now R is given as 8.31 joule per mole into Kelvin. Right? Okay. Now listen. First thing, at STP, the volume occupied by the 1 mole ideal gas is 22.4 liter. Right? But here, the volume of the container is given the 44.8 liter. So, what is the quantity of a gas in given cylinder? First, we have to find out this. Therefore, at STP, volume occupied by 1 mole ideal gas is V is equal to 20.4 liter. Right? Now the volume of the cylinder is 44.8 liter. In cylinder, volume of helium gas is 44.8 liter. Therefore, the mole number of helium gas, mole number of helium gas is 44.8 upon 22.4 is equal to 2 mole. Right? So first we find out the number of mole in a given cylinder having the volume is 44.8 liter. Here the 2 mole helium gas is filled at standard temperature and pressure. Now we have to find out how much amount of the heat is required to rise the temperature of helium gas in the cylinder by 15 degrees centigrade. Therefore, we have the equation of the molar specific heat at constant volume. According to the definition of CV, that means the molar specific heat at constant volume, the amount of heat required to rise the temperature of 1 mole of gas by 1 Kelvin or the 1 degree centigrade. Whatever the amount of the heat required, that is known as the CV. Right? Therefore, first the helium is monoatomic gas. Helium is monoatomic gas. Right? So its molar specific heat, its molar specific heat is 1.5 R. CV is equal to 1.5 R. And at constant volume, the amount of heat required to rise the temperature by 15 Kelvin is Q is equal to mu CV delta T. Mu CV delta T. But from equation 1, the value of the CV is 1.5R, therefore mu into 1.5R into delta T. Now just we find out the mu. Mu is 2 mole into 1.5. Value of R is given 8.31. Delta T is given the 15. Delta T is given as 15. So as we simplify it, we obtain 374 joule. Heat is required. So where is the numerical? Again, here at STP, the helium gas is filled in a cylinder having the volume is 44.8 liter. So what is the amount of the heat needed to raise the temperature of this helium gas in cylinder by 15 Kelvin? Value of R, universal gas constant, is given 8.31 joule per mole Kelvin. Now at STP, the volume occupied by 1 mole ideal gas is 22.4 liter. Already we know it. That is the standard value at STP. Okay. Now, in given cylinder, the volume of helium gas is 44.8 liter. Therefore, the mole number in a cylinder of helium gas is volume of the cylinder divided by the volume of 1 mole ideal gas. That means the 44.8 divided by 22.4. So 2 mole is the helium gas filled in a cylinder. Complete? Okay. After that, helium is monoatomic gas. For monoatomic gas, the value of molar specific heat at constant volume is 1.5 into R. Keep in mind that helium is the monoatomic gas. So its molar specific heat is CV is equal to 1.5 R. And also we know that at constant volume, the amount of the heat required to increase the temperature of the helium gas by 15 Kelvin is, according to the definition of molar specific heat at constant volume, Q is equal to mu CV delta T. But CV is equal to 1.5 R, substitute here, so is equal to mu into bracket, instead of the CV, 1.5 R into delta T. Substitute the value, mu is 2, 1.5, R is 8.31 into increase in temperature is 15 Kelvin. Therefore, 374 joule heat is required. Clear it? Okay. After that, the next. Estimate the fraction of molecular volume to the actual volume occupied by O2 gas at STP. Diameter of O2 molecule is 3 angstrom. Now, diameter of oxygen molecule is D is equal to 3 angstrom. Now, first we find out the volume of one molecule according to the 4 by 3 pi r cube, because in the postulate of an ideal gas we consider that the molecule of a gas is the perfect rigid sphere having the definite volume. That is, the radius first we require, therefore by considering the sphere, so its volume V is equal to 4 by 3 pi r cube, right? And actual volume of a oxygen gas at STP is 22.4 liter. Clear this? Okay. Therefore, diameter of O2 molecule is D is equal to 3 angstrom. Therefore, radius R is equal to D by is equal to 1.5 angstrom is equal to 1.5 convert into meter minus 10 meter. Now, volume of one mole oxygen at STP is V is equal to 22.4 liter. 22.4 liter. That means that 22.4 into 10 is to minus 3 meter cube. That is the volume of oxygen at STP. Evaporated by Na is 6.023 into 10 is to 23 per mole. Number of oxygen molecule. Therefore, volume of 1 mole O2 gas is equal to volume of one molecule 4 by 3 pi I cube into number of molecule in 1 mole gas. So 4 by 3 pi 3.14 into radius is 1.5 into 10 is to minus 10 whole cube. You will get the number 6.023 into 10 is to 23. Thus we find out the volume V dash of 1 mole of gas having the molecule of 3 angstrom diameter. V dash is equal to, as we simplify, we obtain 8.51 into 10 is to minus 6. 10 is to minus 6 meter cube. Therefore, fraction of molecular volume to the actual volume. Fraction of molecular volume to the actual volume is equal to V dash upon V. V dash calculated value of volume is 8.51 into 10 is to minus 6 upon V. Standard volume at STP is 22.4 liter. Therefore, the fraction of the volume is 3.8 into 10 is to minus 4. Again, we have to find out the fraction of molecular volume to the actual volume occupied by the oxygen gas at STP. Diameter of oxygen molecule is given to 3 angstrom. So diameter of the molecule is given 3 angstrom. Therefore, radius is divided 1.5 angstrom. So 1.5 to 10 is to minus 10 meter. Okay. So how we calculate the fraction of the volume? So here in 1 mole the number of molecule R is equal to Avogadro number. Here the diameter of one molecule is given. Therefore, volume of one molecule into number of molecule in 1 mole. That gives the volume occupied by the given gas. 1 mole of given gas. And also, the standard volume at STP is already we know it, that is the 22.4 liter. Take the ratio of calculated value and standard value of the volume. That is done. Now, volume of 1 mole O2 gas at STP is 22.4 liter. That means the V is equal to 22.4 into 10 is to minus 3 meter cube. Avogadro number is this. Therefore, volume of 1 mole O2 gas, actually that is the molecular volume, is equal to volume of 1 molecule into number of molecule in 1 mole gas. So 4 by 3 pi I cube into Na. So as we substitute the value, so we obtain the molecular volume V dash is equal to 8.51 into 10 is to minus 6 meter cube. Now, the fraction of molecule volume to the actual volume is equal to V dash upon V. calculated value upon standard value. So fraction of the volume is 3.8 into 10 is to minus 4. Clear it? Oh. After that, the molecular volume is the volume occupied by 1 mole of an ideal gas at STP. So that is 22.4 liter. So first thing, at STP, at standard temperature and pressure, the pressure P is equal to 1.013 into 10 is to 5 meter cube is equal to 1 atm, 1 atmospheric pressure. Temperature T is equal to 0 degrees centigrade. That means the 273 Kelvin. 273 Kelvin. Universal gas constant R is equal to 8.314 joule per mole Kelvin, joule per mole into Kelvin, and mu is given the 1 mole. Mu is given as 1 mole. Now from the equation of state PV is equal to mu RT. Now what we have to find out? The molecular volume is the actual volume, or the volume occupied by 1 mole of any ideal gas at STP. Right? Therefore, for an ideal gas, equation of state PV is equal to mu RT. PV is equal to mu RT. Okay. Therefore, V is equal to mu RT upon P. Substitute all value. Mu is equal to 1 mole, R is 8.314, temperature 0 degrees centigrade or the 273 Kelvin, upon pressure 1.01 into 10 is to 5. Thus we obtain 22.4 into 10 is to minus 3 meter cube is equal to 22.4 liter. We have to prove this thing. This volume, or the molecular volume, is the volume of an volume occupied by 1 mole ideal gas at STP. It's same, and that is the 22.4 liter. So that is the volume occupied by the 1 mole ideal gas at STP. Now after that, we are also considering the numerical 13.6, also 13.6. 13.6 is estimate the total number of air molecule, inclusive of oxygen, nitrogen, water vapor and other, in a room of capacity 25 meter cube at temperature 27 degrees centigrade and 1 atmospheric pressure. Now keep in mind that the pressure is given 1 atmospheric pressure, 1.01 into 10 is to 5 Newton per meter square. That is the value of pressure. Now room temperature T is given the 27 degrees centigrade. Therefore 27 plus 273, 300 Kelvin. Volume is given 25 meter cube. Now we have to find out the total number of air molecule in this volume of a room at 27 degrees centigrade and 1 atmospheric pressure. So from equation PV is equal to mu RT, from equation PV is equal to mu RT. Right? But we know that the bulk mole of an air, there is our equation 1. Number of mole in air, or the air of air, is mu is equal to N upon N, N upon N. Therefore, n is equal to mu n. N is equal to mu n. That is our equation number 2. Now our equation 1. Suppose we substitute the I is equal to kb into n. kb into n. So mu na kb t. That is our equation 1. Clear this? Okay. Again, from equation 1, PV is equal to mu RT. We substitute the value of R. R is equal to Na into Kb. Evaporated number into Boltzmann constant, that is equal to R. Right? But the number of mole of A is mu is equal to n upon Na. Therefore, n is equal to mu into Na. We require the total number of A in given volume of room. From equation 1, mu into Na is equal to PV upon KBT. PV upon KBT. That is our equation number 3. Again, our equation 1 is PV is equal to mu RT. Here we substitute the value of R is equal to Na into Kb. Therefore, mu Na Kbt. And number of mole of an A is mu is equal to n upon Na. Therefore, n is equal to mu Na. So from this equation 1, mu Na is equal to PV upon Kbt. And from equation 2, n is equal to mu Na is equal to PV upon Kbt. Substitute the value of P, 1.01 into 10 is to 5. Volume 25 meter cube. 25 meter cube upon Kb, Boltzmann constant 1.38 into 10 is to minus 23. Temperature T is given to 300 Kelvin. 300 Kelvin. Thus we find out the number of molecule is 6.10 into 10 is to 26. Number of atoms or the molecules in a group. 6.1 into 10 is to 26. Okay, there is the number of mole. Okay. Now again, there is the very easy numerical. We have to find out the total number of molecule in a given room, having the volume is 25 meter cube at temperature 27 degrees centigrade and 1 atmospheric pressure. Pressure is given 1 atmospheric, therefore 1.01 into 10 is to 5 Newton per meter square. Temperature is 27 degrees centigrade, therefore 300 Kelvin, and volume of the room is 25 meter cube. Right? Now we know that the equation PV is equal to mu RT. So substitute the value of R, mu into value of R, Na into Kb into T. Therefore mu Na Kbt. So from this equation, mu into Na is equal to PV upon Kbt. This equation. Now, number of mole in A, mu is equal to n upon Na. Therefore, n is equal to mu Na. Comparing these two equations, or n is equal to mu Na, but mu Na is equal to PV upon Kb into T. Substitute the value of PV upon Kb into T. Pressure 1.01 into 10 is to 5. Volume 25 meter cube. Boltzmann constant 1.38 into 10 is to minus 23. Temperature 300. Thus we obtain the number of molecule in a given room is 6.1 into 10 is to 26. Clear this? Okay. So very easy numerical. Most of the numerical is depends on the equation of state. PV is equal to mu RT and also the equation of the specific heat, molar specific heat.